Okay, so the focus of my talk today is to sort of suggest that a smart city can address COVID-19 simply by using the cell phones of its inhabitants. And a big thing here will be how you record the coughs to train a data set, and then how you're going to use it. That's one of the big things that's pending. But I'll also first tell you a bit about the intellectual merit of the solution, meaning how can recordings of coughs actually result in good diagnostic measures. Here you see a bunch of papers that have come out this year. All of them are related to the subject of the topic of today. And these are the samples, these are, one of them has COVID with symptoms, one doesn't have COVID, and the other one is asymptomatic COVID. Very hard to tell, but you can actually see the difference here. So this is an example of two baby coughs, and we can tell them very easily. What we found seems to indicate that coughs are a bit like, if I cover my voice, my nose, my voice is different, and humans can pick it up. Or if somebody is just has just awoken, you can say, oh, it's a morning voice. And we've shown that AI can detect a COVID voice fairly well. Okay, and so this is one type of vehicle, and this comes from research in the lab, where we've shown that just by listening to the air filter, you can tell whether you need to change the filter or not, just by listening with a cell phone to the sound of a car. And that, again, it's a bit similar in the sense that any human in any car, regardless of the number of people in the car, can tell if a window is slightly open or not, just by the buzzing noise, or if you have a flat tire or you're going on overdrive, but you cannot tell this. So it's an analogy, and it was part of the inspiration. These are researchers from our lab. And then there is now some work also on what's called the liquid biopsy. And it's a bit the same thing. Just by collecting blood, you can tell whether there's cancer by looking at the cells in your blood, and you can detect them like very, very early on, just as soon as they start forming. That's ongoing research. And one of the key insights that we had is, let's collect a lot of data, and that comes from GPT-3. That's a model that's using a lot of data. They have 1.5 billion parameters, and if you look at here, this is the training petaflops per day, and this GPT-3 is way more than anything has been done before, by at least one order of magnitude almost. And they apparently they spent like $5 million just in electricity. And so our idea was, well, that basically they took all the text that's ever been written by anyone and they process it. And we said, well, what about if a city takes all the coughs and shares all that data? And so that's the idea of the MIT Open Voice project is, let's try and build a tool that lets you talk to a web page, very much like you talk to a person. And our vision at the lab, in my lab, we not me, but the term Internet of Things was coined there, and now we're working on building tools that let you talk to anything, and that requires getting a lot of samples, and that's a bit the idea. And you can go to opensigma.mit.edu and donate your cough, and hopefully every city, imagine if everyone in a city did this, we would have in 5 seconds a huge database like the one we did, a crowdsourcing approach, and I think we have the biggest database of health information ever recorded, ever crowdsourced, and we have several 100,000 coughs. And so we published a bit this idea in a paper, and you can read more about it. It's sort of a new artificial intelligence approach, and that's the idea, that you collect all the coughs, and if you can do longitudinal and you can track the coughs in a city, you can see where things are evolving in terms of the pandemic, and that's a bit one of the goals that I think a smart city project around this idea should have. And there's a lot of issues that need to be addressed. One of them is the bias. This is I forgot to add the reference, but you can search this. It's not my research, but shows some of the bias of these algorithms. And there's also going to be bias with the coughs, and we've seen them. We've shown that you cough in your own language, and so if there's only coughs of one language, the results will be probably better for that language. We have like more female than male voices, so that's another type of, because they're just apparently a bit more generous in the crowdsourcing effort. And all of this needs to be taken into account, so that there's a number of things. And I talked on this Viewpoint article about things that can be done, and in particular, how could we sort all this data of a city without violating, privacy rules. And so this is a bit the idea, and I'm conscious of time, so I'm going to try and wrap up in 5 minutes. But this, I don't know why it keeps skipping. Okay, so the idea of this approach is first to create orthogonal biomarkers that can serve for many conditions, not just COVID-19. And we've proven that you can use the exact same biomarkers for Alzheimer. And so I think a smart city that is able to track not just COVID-19, but other diseases, I think will be a much more healthy city. And so that's one of the goals. Then there needs to be some sharing approach in the city with agreements in place as to with whom you share it, who can do prototypes, and who owns the data and the resulting models. And then you need a specific model and to train, and that's going to take a lot of computational time. So one needs to think about what's the best way to approach this. These are the results that we got for COVID-19. At the bottom, you have Alzheimer. And the important thing here is that for asymptomatics, so no symptoms official, we're getting 100% of detection. This means that there's no false negatives. Probably we have some false positives, meaning our tool needs to be validated with hospital data, and I think would need to be validated by a town, because we found that there's many localization biases that we think may play an effect. But here you have 17% false positives. So basically the tool, if you're asymptomatic and the tool tells you you don't have COVID, you're most likely not to have COVID. There's a few exceptions, but that's a bit the idea. If it says you have COVID, it may be a true positive, or it may be a false positive. And sort of similar results for Alzheimer. And that's a bit the results on the overall. So if there are symptoms, it's not 100%, it's 98.5. So it's not as good. And you can use the tool to very reliably look for groups. So instead of asking for one COVID positive, you ask for a few in a group, then your accuracy can be a lot better. And in one of the papers, the IEEE one, we detail this a bit in a figure how this is calculated. But the idea is depending on the accuracy, you can get more or less. And this is sort of like a pool testing. So you can imagine a city doing pool tests in different areas and finding out the areas where the pandemic is growing and then putting subsequent testing there. This is just the hardware we used. This talks a bit about the model, and we don't have a lot of time left, but we used a model of the brain developed by the MIT Center for Brain, Minds and Machines, the CBMM Center, and that's the model. It has like 4 units: the sensory stream, the brain noise, the cognitive core, and the symbolic compositional models. And we use a collection of biomarkers. These are the ones that we use for COVID, and we also try them for Alzheimer. And what's interesting is that these different biomarkers, each of them was trained using a different database. The thing is that they detect different patients. And if you look at the overlap between 2 biomarkers, there's almost no overlap, like if they were sort of orthogonal, I said. And there are some which are in all of the 3 biomarkers. So this is not a perfect analogy, but it points to a direction where maybe we can find biomarkers that are sort of independent of each other to follow different kinds of conditions. And in the case of Alzheimer, we use 12 biomarkers. And here you can see in dark orange all the people that were Alzheimer positive. So this is just for Alzheimer. And in green, the ones that didn't have it. And you can see, we call this a saliency map, and hopefully this can be used for longitudinal tracking. Okay. And yeah, so I think just to very quickly finish the next slide. So here, this talks a bit about how the different biomarkers would perform based on various transfer learning conditions. So that speaks to the importance of cities not building just one model, but trying different models and being able to sort of own the whole supply chain of data, the whole pipeline, so you can do different models and find out which one is better. So anyway, I'll be glad to take questions.